Hello, today we're going to solve a problem using Newton's second law and see how it works in practice. An aircraft flies from an aircraft carrier, gaining speed from 0 to 250 kilometers per hour in 2 seconds with the help of a catapult. If the average force acting on the airplane is 9.35 hundredths times 10 to the 5th power of Newton, what is the mass of this airplane? Let's write down the terms of the problem. We're going to have to determine the mass of the airplane. And we know the initial velocity of the airplane, 0 kilometers per hour, and the airplane's terminal velocity is 250 kilometers per hour. The time it took for this velocity change to occur is 2 seconds, and the average force acting on this airplane is equal to 9 whole 35 hundredths to 10 to the 5th power of Newton. If we look at this problem, we see that the velocity in this case has been given to us outside the system unit, so we'd better convert the velocity to meters per second. To do that, I remind you, we have to divide the velocity value by 3.6 tenths, and then we get a value of 69 whole 4 tenths meters per second. And now our task is to chart the motion of this airplane. If we apply Newton's second law of motion, given that the velocity changes by the action of a certain force, then of course we have to write down this law. We'll apply it in the form derivative of this law, that is, by describing the force that acts on this object. The force is mass times acceleration. If we look closely at the problem, we can see that the acceleration that this airplane has received can be described by the change in its velocity, because the acceleration is the rate of change of velocity of the airplane. To do that, we'll remember acceleration as the change in velocity of a given object per unit of time. And from this formula we can calculate the mass of this airplane. To do that, we multiply the force by the time and divide by the difference between the final and initial velocity. So we've got the final formula. So now our job is to put in the numerical values. The force is 9.35 hundredths by 10/5 of a Newton multiplied by 2 seconds and divided by the difference in velocity, but here we're left with a terminal velocity of 69.4 tenths meters per second. So after doing the math, we get a mass value of about 27,000 kilograms. For an airplane, that's a pretty normal mass value, and so we can see that here in this kind of problem we can see not only the application of Newton's laws but also the laws of kinematics. We have to be prepared for that because we have to describe the acceleration also through quantities of kinematic character. So, the second task. When two people push a body of mass m in one direction, it acquires an acceleration a1. When one of these people pushes this body in the opposite direction to the first one, the body acquires acceleration a2. Determine the force with which each person acts on the given body. So, the challenge is that we have to determine the value of the force that each person exerts to a given body. We know that the body has a mass m and receives different accelerations depending on the direction of the force. Let's show in the figure how it will look like. So the first situation. The object experiences the action of two forces directed in the same direction. Let's show it in the figure like this. Then we can write down Newton's second law taking into account the action of these two forces, and specifically their resultant force, which we define as the vector sum of these two forces. In this case, given that the forces are co-directional, the resultant force will be defined as the sum of the moduli of these forces, which we immediately describe with regard to their directions. And then we get the product of the mass of the body by the acceleration in the first case. What happens in the second case? one of these people starts pushing this body in the opposite direction. Let's assume that the force F1 remains acting in this direction. And in the opposite direction, the force F2 starts to act. And the body now gets acceleration. We don't really know in which direction, because we don't know the relationship between these forces. Which one is greater, which one is less. But let's assume that the acceleration is to the right. That will be the acceleration, a 2. Then it turns out that the difference between these forces, given that the force F2 is in the opposite direction, now it's reversed, will be equal to the product of the mass of this body and the acceleration of a 2. We thus get two equations in the system, which we just need to solve with respect to these two forces. For example, we want to find the force F1. What do we do to do this? We add up these two equations and we see that F2 cancel each other out in this case. So then it turns out that 2F1 will be equal to the sum of these two parts, MA1 plus MA2. Here we can take the mass as a common multiplier, and we get in parentheses the sum of the acceleration data. From here we get the value for the force F1. Divide by 2. For the second case, we now subtract the second equation from the first. F1 cancel each other out. F2 here gets a minus sign before the minus, so let's write it down like this. On the right hand side we get difference of these expressions. As a result, we get here the doubled force F2. And here we can also take the mass out of the bracket. Then we get the expression that F2 will be equal to m times A1 minus A2 and divide by 2. So we have the value for the two of these forces that are acting on these objects. This is a practical application of Newton's second law. When there is one force acting on a body, or there can be two, and of course in the future we will encounter problems where forces act on the body, which are differently directed, and of course you'll have to work with the projection of these forces too. Well, I'll say goodbye for today, and I'll see you in the next lessons. Goodbye.